Thanks all of you for joining us today. It's a nice day outside, so yeah. Anyway, so the OT. Today, Ashley and I, we are going to talk about the OT. This is the observing tool, the software application that you are going to use in order to submit your proposal to ALMA. In this first part, we are going to do the easy part. So first, credits to all the people developing the tool and to the people, the users from the community that have been also helping with the tests and everything before the release of this year's version. From where to obtain it, you can go to the red link in this slide. There is information there also about the new release. There are in the previous versions there were some issues with Java. Not anymore. You don't need to worry anymore about that. It seems that this release has its own installation of Java. So in this website you can go either for the installer version or the Tarball version. The Tarball version is a manual install. You have to do everything. The installer version is the one that is recommended. It will be installing everything very easy. So once you click in the installer, you are prompted to this new other website where you can select according to your OS distribution, and from there you then proceed to download the OT. So once you finish the download, you will start the installation. This is pretty straightforward. And one thing that you need to take into account is that if your project is going to have a lot of science goals, you will like to use more memory in your installation. So if you foresee that, you can choose from the first installation. If that is something that happened during the project preparation, you can always save your project, save it, and make the installation again with more memory. So once you install it, you are prompted to a new window. The top in the top here is the startup options, and then you are asked if you want to create a new proposal or a DDT proposal, or if you want to retrieve actually one proposal from the ALMA archive or from your local disks. And then when you are done with that part, you are presented then with this window in the big window here with the 3 panels, and you will see that these 3 panels of these 3, the first one is the one where you can navigate through your entire project, different science goals, as Ashley is going to show later. In the second panel is where all the forms that you need to fill in are going to appear. So this is the panel where you are going to be interacting with the tool. And in the panel number 3 is where all the warnings, errors, and also information on how to solve those mistakes or errors can be found. Then we go to the proposal level in the first panel, and in that proposal level then we go to start including the information about the project. So in this case it's just general information. We get to be shown, we need to include the proposal title, the abstract. You can leave it for later, but don't leave it for the end. The proposal type, scientific category, all of this information that is crucial for your proposal should be input in this panel. However, if you always have doubt about anything, about what this means, I don't know what to put here, there is always one question mark. I'm just trying to remove you guys from my slides. Done. And then in the top corner you see that there is one box with a question mark inside. Every panel in the OT has this question mark, and is very useful because once you click it, it will show information about the panel that you are working in. In this case, it shows what are the definitions of the different proposal types. So if you are downloading the OT and you still don't know what the proposal type you are going for, this is the place where you are going to make your mind. You can change from regular to large depending on the science case, and in the amount of time you are requesting on the main array or in the ACA array. Anyway, this information is here for you for checking. This is the manual, actually, the manual of the OT. Okay, so next, after choosing that, you go to scientific category. Again, there is one question mark that will give you information about how to input the information there. Then you select the keywords that of your proposal, and then in the next step is the investigator session, right? In this session is where you need to start including information about your collaborators. In this version, there is this new column that is called reviewer. As you can see, it is ticked. It doesn't matter if your proposal is going to be reviewed by a panel or by the peer review process. You always have to select one option there. So remember that that person is going to be in charge of reading the 10 proposals that are associated to the submission of this proposal. So further down in that same panel, then you will find the reviewer information. We have been speaking about you need to update your information, go there and update your information. Yes, you can do that actually following that blue link that is in the reviewer information block. And in there you can specify if you are a PhD student and you are identifying your panel, your mentor. Then you do that here, and after that, you need actually to update your information. Then if you click actually in that blue link, you are prompted to the science portal, and here is where you need to update your information about those keywords that you need to choose to get more proposals to read for the process. Okay, so once you do that, you need to upload the PDF of your proposal. If it is a regular proposal, there is up to 4 pages. Put there the best science case that you can think of, good picture, good figures, good tables, everything clear, and for sure you are going to get a good rank. I don't know if you are going to be observed, but a good rank you get. And then the last part is the duplicate observations. Please make sure that the idea that you have and you are going to propose to the telescope has not been observed before. And to do that, you can check actually in the duplicate information box that is in this panel. There is in the second blue link that is in there. You can actually check if there are projects that or the position on the sky that you are going for has been observed before. And in the bottom, in the blue column that is in this website, in the bottom, you can see that you can check the ALMA Science Archive. You can check also, there is one table with the projects that are currently in the queue of the telescope. So you can also cross-check if something there is related to what you are going to do, and make sure that your proposal is not a duplication. Okay. All right. So from here is the creation of the field science goal, and here is Ashley who is going to explain on this part. So thank you very much. I will stop sharing here once I see my mouse. Wait, perfect. And then Ashley, it's on you.
All right, thanks, Andres. Okay, for the second part, I'm going to be showing you how to set up a science goal. And I want to point out that what I'm showing you is very specific. So I'm using an example of a spectral line observation that is going to be a mosaic, but every proposal will have its own unique setup. So keep that in mind, that there's going to be a lot that's not covered in this talk. For example, I'm not covering single continuum spectral scans, BLBI observations, or polarization. Okay, so at this point, you'll want to add a science goal, and you can do this a couple of ways. So under planned observing, you can right click and just put a new science goal in, or you can up in the top panel, just press the appropriate button and put a science goal in that way. once you've done this, you should see 6 more sections underneath the science goal that you have chosen. And the first section that you'll see is the general section. And this is where you're going to give your science goal a name, and you can also put in a short description. So in this example, I have given it a unique science name that includes the transitions that we're observing, that it's a mosaic, and the target. And within the description, in this example, I am including the integration time for this science goal, as well as the sensitivity we want to reach, and the resolution. So the next panel or section that you will see under the science goal is your field setup. And so in your field setup, you are going to be putting in source information, and this is also where you can adjust your pointings or the orientation of your mosaic. So we'll start off with how you put in source information. So you can see that under in this panel, there is a place that says source name, and you can actually type in a source name here and hit resolve. And the OT will actually query Simbad for you and get you information on your source, including RA and DEC and the radial velocity and redshift. And so you'll see that it's been populated where the arrow is pointing. And then below this, we need to put in source properties. And these are the properties that you expect of your source when you are actually doing the observation. So you want to put the peak flux density per beam. So either peak continuum flux density or the peak line flux density. And these are important because they're used for the OT to make sure that the sensitivity you're reaching makes sense. And if you're doing a line observation, you also need to put in a line width. And similarly, the OT will make sure that you are properly resolving the line when you calculate the sensitivity that you need to reach, and you specify a bandwidth when you do that calculation. And it will require that you can actually get at least 3 channels across your line. And so just to point out, each science goal can have multiple sources. And if you want to put in another source, you just go to the field setup tab and you hit add source, and you put in the same information for that source. But in this example, we're only interested in one source, and that's NGC 3256, which is a nearby merger. And so I mentioned that we can actually use the field setup to specify the pointings or the mosaic extent and orientation. But one thing that you will want to do is to have an actual image to compare against. And the OT will is able to query a number of catalogs and pull up an image of your source for you that you can use as a reference. So when I do this for NGC 3256, I end up getting an image like this. I also want to point out that you can input your own FITS file here, and this actually might even be more useful for people who are doing molecular line observations, because then you can actually see the extent of molecular emission in your source. Now, I've also drawn on here a green rectangular region. So this is the mosaic, the extent of the mosaic that I would like to map out in NGC 3256. If you wanted to do individual pointings, you would instead select the circle with the X in the center of it, and you could then put down individual pointings. But I would like to do a continuous mosaic, so I have selected the rectangle, and I've put down the rectangle at the extent that I want it to be, and I've rotated it. And you can rotate it by clicking on the green box in the corner and moving it around. So at this point, you won't be able to see any of the actual pointings because you haven't put in spectral setup information. And the OT needs to know what frequency you're observing at so that it can determine the size of each of the pointings. So the next section that we're going to look at is the spectral setup. And this is what you'll see before you put anything in. You'll see all of the bands and what frequency they correspond to. This is a nice visualization of each of these bands. And you can also see the atmospheric transmission, which is shown here. And that's also useful because it's showing you essentially where there are atmospheric absorption lines, which you really want to observe. You want to avoid observing when you're setting up your spectral setup. And then below this, you can actually specify the type of observation that you want to do. And we want to do a spectral line observation. So we've selected that. And one other thing I want to point out before we move on is just above this, you can specify the water vapor column density. And in this example, I've specified the first octile, but in most cases, you want to keep this as an automatic choice. Now, if you scroll down, you'll actually see where you can input the spectral windows. And there are 4 basebands, and each of these basebands can have 4 spectral windows in them. And you can input a spectral window manually, or you can choose to center that spectral window on a line. And if you choose to add a spectral window centered on a line, the OT will actually bring up a catalog that you can search for the line that you're interested in observing. So under transition filter, I've typed in HCN, and there is a wildcard star at the end of it, so it will search for any HCN transition. You can use wildcards in these searches to essentially avoid having things that you don't know what you want to put in for the observations. Then you can see it pulls up this list of HCN transitions for us. And that includes transitions in all of the bands. And so I'm actually interested in the 4-to-3 transition. So I want to specify this transition, and I will select it from the list. And when I select it from the list, it will go into the spectral windows in this baseband box. And then you'll see that actually the OT is only showing you this transition. And that is because it's filtering out unobservable lines. And once you've specified a transition, it knows what frequency it wants to put the local oscillator at, and it has already decided where it's putting your upper and lower sidebands. So based on that information, it can then determine what other lines are observable within those sidebands. And this is, or within that spectral window, within that baseband. This is telling us we can only observe HCN in this spectral window. So once you have selected a line here, you will see it come up in your baseband, and then you'll need to specify a spectral resolution for this transition under the bandwidth here. And you can specify a number of different resolutions. And if you want to do a spectral line observation, you probably want something that's going to be below the continuum, the default continuum observation line width, which is channel width, which is much broader. The other useful thing that this puts in here are the frequencies. So you have the rest frequency of the transition, which is the left frequency that's listed here. And then on the right, you have the sky frequency. So the OT has taken the redshift of your source and calculated the redshifted frequency that you actually want to do the observations at. And you also can specify how much spectral averaging you want to do. So here I've specified 2. I'd like to average over 2 channels, and this will have the benefit of reducing the data rate. And you actually don't end up losing a factor of 2 resolution. So it's a good thing to consider doing for your observations. So once we have that in, our OT has put down the local oscillator, which you can see here in band 7, and we can see where the HCN spectral window is now located within that baseband. And now I'm going to show you what it looks like if I fill something in each of the basebands. But I want to highlight here where it says fraction. So in this situation, I have chosen to just put one spectral window in each of the basebands. So it's using the full bandwidth. But you can actually choose 1/2 or 1/4. And just keep in mind that this is going to impact the maximum resolution that you can reach in your spectral window if you choose to put more spectral windows in there, but there may be setups where that is actually useful for you. Now, I've also put in HCO plus here, which is at the top, because the OT will automatically order your spectral windows in each of your basebands by decreasing frequency. At the bottom two basebands, I have just put in 2 continuum spectral windows, but I've maintained the higher channel resolution. And I'm doing this because we encourage PIs to optimize the observations that they're doing by essentially not wasting any of the basebands that you can observe in. For this observation, I'm just interested in HCN and HCO plus 4 to 3 transitions, and I'm not sure what else I want to put in. So I have just simply specified 2 other continuum spectral windows in the 2 additional basebands here. Okay. So once you have that set up and you zoom in to take a look at the spectral setup above, this is what you'll see. So you can see the 2 continuum windows in the lower side band, and you can see the 2 spectral windows in the upper side band. Now, the one thing that I want to highlight here is that if you have a line that ends up being too close to the edge of a sideband, then you will need to shift that spectral window so it's not spilling over the edge of the sideband, because it's not observable like that. So in this case, I have offset the HCN spectral window and from the line so that it's within the baseband, and that should be fine because these are fairly large spectral windows and we'll still be getting all of the line for this source. And so now we can go back to our field setup and we can see the pointings of our mosaic. And in this case, for band 7 frequencies, we're getting 8 pointings. And just to highlight here, the pointings go beyond the rectangular region of your observations, but the region of highest sensitivity will be within the green rectangular region that you're showing here. So you really want to make sure that you're encompassing all of the regions that you want to detect within that green area, even though you're getting this additional extent from the outer edges of the pointings here. Now you also see calibration setup, and in most cases, you should just keep the default calibration and just use the system-defined calibration. But if you do choose to do a user-defined calibration, you must justify this in your technical justification. Now, within the control and performance section, this is where you're actually going to get your time estimate for your observations. And at the top here, you will see information of available configurations. So it shows you available ACA 7-meter configuration, and then it will show you the 2 extremes for the 12-meter configurations. You have the most compact to the most extended. Above that, you have beam size and the number of antennas as well. And so in this information, you can see the beam size that you get in each of these configurations, and you can see the sizes of the baselines, and you can also see the maximum recoverable scale. So all of this information is important because it is going to limit what you can actually specify below this. So in this example, I have specified that I would like a single resolution, but you can actually do a number of things like specify a range, or if you hit any and it will decide, or it will come up with a list of potential observations that will reach the sensitivity that you specify below. But in this case, we specify single, and I want 0.9 arcsecond resolution. And in my source, the largest structures that I want to observe are at 5 arcsecond scales. And this is good because this is below the maximum recoverable scale of the most compact 12-meter configuration, which will allow me to still do my observations. And because this is a line, because we're doing line observations, the bandwidth that I've used for the sensitivity is one that I've defined myself. So the default is either the full bandwidth of the spectral window, or it is the channel width of the spectral window. But we don't necessarily have to use those specified values. We can actually decide what bandwidth we want to use for our sensitivity. And in this case, I have chosen 10 kilometers per second. This is another galaxy. The line's pretty broad, so this should allow us to get at least 3 channels of this size across the line that we're interested in. So once you've specified all of this information, you can then hit the time estimate, and it will come up with something that looks like this. And so for this example, we have 13.6 hours required for observations. It will show you the possible configuration that you can use. So here I only have one, C43.1. And then below this, you have a breakdown of what of the time that's going into this total time for the science goal. And finally, you'll want to justify all of the choices that you've made in the OT in the technical justification. So it breaks down the sensitivity that you have here. And this is where it's going to check if you are properly resolving your line with the bandwidth that you use for sensitivity, for example. And it's also checking if you have a good enough signal to noise. So for the peak line flux that I specified, I will be getting a signal to noise of 10 with the sensitivity that I've requested. Now, within the actual justification, you should explain how you determined the required sensitivity. So, for example, in this example, we reference some papers that we've looked at to determine how to get to an estimate of the 4 to 3 line, because in this case, we're assuming that, or we know, because we've checked the archive to make sure there aren't observations of this, that we can use this literature value to compare against observations that have already been done, such as the lower J transitions of HCN. And then you want to make sure that you are able to observe all of your sources, including your weakest source. So if you would like to, you can mention that in your technical justification. You also want to talk about the resolution that you have chosen, and you want to justify why you have specified this resolution. So, how extended are your sources, or how compact are they, and why do you want to reach these scales, but from a technical standpoint. And finally, you will see that here at the bottom, you need to justify the correlator setup that you have chosen. So why did you choose the spectral resolution, and why did you choose to bin the channels or do averaging over the channels and so on. And you need to justify this for the data rate that you end up with. And I also want to highlight that this section will look different if you have different kinds of observations. Specifically for VLBI, this will look very different. So these are just examples of what you might get for a spectral line observation. And it's also similar if you're just doing a continuum observation. So once you've set up your OT and the science goal, you want to validate your proposal if you don't want to add in any other science goals. So you can do this by going to the file and then clicking validate, and it's going to check your OT for any issues that you need to clear up before you can actually submit your proposal. And this will be shown down in the bottom panel that Andres had pointed out before. And so for this example, it's saying that there's no mentor defined and nobody has a PhD. So they clearly can't submit this proposal if you don't have a PhD. So you need to make sure you fix that before submitting the proposal. Then you can revalidate, and once you end up without any issues and you've checked the OT, you can then submit your proposal. So that's it for how you can set up a science goal. And at this point, you can review everything and submit your proposal. Andres and I can now take questions for the things that we've presented.